All right, class, today we're going to be talking about angles. And I know we've been dealing with angles already in circles, but we're going to take a look at a special type of angle called inscribed angles. Before we go over the definition, let's take a look at Geometry Sketchpad and look at something. So we've been dealing with arcs that are on a circle, and we've been looking at the measure. Here's the measure, here's arc AB. And it's the minor arc, and as you can see, the measure of arc AB is 63.54. And as I move A and B closer together, the measure of the arc decreases. And as I move them farther apart, the measure of the arc increases. But how do we get this measure of this arc? Not the length, but the measurement of the arc? Well, we got that by basically looking at the angle that produced that arc. And as you can see here, this angle is called a central angle because the vertex is the center of the circle. And if you can notice, the relationship between the central angle and the arc is that the arc measurement is the same as the central angle that produced that measurement. So as I change and move A around, I get that same relationship as well. So now we're going to take a look at another type of angle that's in a circle where the angle is not, where the vertex is not the center of the circle, but where the vertex is on the center of the circle. So let's get rid of the central angle and let's take a look at an angle where the vertex is a point on the circle. And so we call these type of angles inscribed angles. And as you can see here, now we have a different angle because now the vertex is no longer on the center of the circle. The vertex is on the circle. So this is an inscribed angle. And let's take a look at the measurement of the inscribed angle and the measurement of the arc that is produced, AB. Anybody notice a relationship between the measurement of the arc and the measurement of the inscribed angle? Let me move A around and see if you notice the relationship. Anybody notice the relationship? Well, if you said that the relationship is that the arc measure is double the inscribed angle measurement, or the inscribed angle measurement is half the arc measurement, you are absolutely correct. So the rule with the inscribed angle is that the inscribed angle is equal to 1/2 the intercepted arc. But I don't want you to confuse the inscribed angle relationship with that of the central angle relationship, because the central angle relationship rule is that the central angle measurement is equal to the intercepted arc, whereas here the inscribed angle measurement is equal to 1/2 of the measurement of the intercepted arc. Now let's take a look at another angle that produces or the results in the intercepted arc of AB, and that angle is ADB. And as we can see here, ADB produces also the arc AB. And let's look at the angle measurement of ADB and ACB, and as you can see, they're the same. So even though C and D are different positions on the circle, because they both share the same intercepted arc, then that means that their angle measurements must also be the same. And so we're going to come and look at that a little bit later. So the vocabulary that we've been using is the vocabulary listed on page 157. They're new words, but we've talked about the inscribed angle. We've also talked about the intercepted arc. And in earlier activities, we talked about the inscribed polygon. And that's where all the vertices of the polygon lie on a circle. And then there's a new word that we're going to use called circumscribed circle, and that's a circle that contains the vertices of an inscribed polygon. So these two relationships, they feed off one another. So let's take a look at the theorems on page 264 and 265 in our note-taking guides, and let's see if we can go ahead and fill this in based off what we know from the activity. So the measure of angle ADB, which is the inscribed angle, is equal to 1/2 the measurement of what? And if you said the arc AB, you're absolutely correct. When I move this out, oops, that's what we should put in there. the arc AB. Okay, and now let's take a look at theorem 10.8. It says if two inscribed angles of a circle intercept the same arc. So as we can see here, this is the intercepted arc, but here we have two different inscribed angles because they're in different positions. So the measure of angle ADB, what's the relationship between that and the measure of the other inscribed angle? And if you answer that it's congruent, you're absolutely correct. Okay. Now let's take a look at another theorem, 10.9. Let's take a look at this triangle, and one thing you can say about this triangle, it looks to be like a normal regular triangle. And let's inscribe this triangle in a circle. In other words, find a circle where all the vertices of the circle, all the vertices of the triangle are on the circle. Well, if you guys remember, we can do that easily by creating perpendicular bisectors of all of the sides of the triangle, and then finding the intersection of the perpendicular bisectors, and that is the center of our circle. So if we hide all the perpendicular bisectors and keep the center of the circle, and then define our circle with this is the center, and let's say the this vertex C is on the circle, you notice that also vertices A and B are on the circle, and that's because we've created it as such. So let's take a look at the angle measurements of this triangle. And as you can see here, we have an acute triangle. Let's see what kind of triangle we have when one of the sides of the triangle passes through the diameter, the center of the circle, and becomes a diameter. What do you notice? And I can't do it exactly, but you notice that now we no longer have an acute triangle, but we have a triangle that's very close to a right triangle. And as you can see here, so when we have a side of the triangle being a diameter of the circle, then guess what kind of triangle we have? You're absolutely right if you said right triangle. So in conclusion, we have a right triangle when a side of the inscribed triangle is a diameter of the circle. And when a side of the inscribed triangle is not a diameter of the circle, then we no longer have a right triangle. So let's go back and fill in. So theorem 10.9 says basically the same thing. If one side of an inscribed triangle is a diameter of the circle, then the triangle is a right triangle. And the angle opposite the diameter is the right angle. So over here, the measure of angle ABC is equal to 90 degrees if and only if AC is the diameter of the circle. So let's look at an example from a checkpoint. They said that a right triangle is inscribed in a circle, and the radius of the circle is 5.6 centimeters. What's the length of the hypotenuse of the right triangle? Well, some of you may say, well, if the radius is 5.6 and the diameter is going to be twice the radius, that means the diameter is 11.2 centimeters. But what does that have to do with our problem? Well, based off of the theorem that we just talked about, so as we can see here, the diameter in this case is 11.2 centimeters. But since we already have a right triangle, that means that this diameter is also the hypotenuse. So that means the hypotenuse is also 11.2 centimeters. So in the interest of time, we're not going to go through all the answers for part B, but I want to say here that we have actually here in this example for number 5, we have two types of angle. We have two different inscribed angles. As we can see here, we have this inscribed angle, which is a right angle, and notice that relationship. If this is 9 degrees, and what does that make this? And then over here, we have another inscribed angle, which is angle D. And here they tell us this is 96 degrees, so what does that make the other arc? And so that's interesting to note. And then we can solve A and B since we have here a quadrilateral, which means it's going to sum to 360 degrees. If we can somehow figure out what this arc is, this angle measurement, and what this angle measurement is. So let's take a look at some other types of angles. We've talked about central angles and inscribed angles. Let's talk about angles that are formed by a tangent and a chord. And as we can see, here's an example of an angle, a tangent line, and a chord. And as you can see, they intersect where the angle is partially in the circle. Let's see what the relationship between those. So here's the measure of the arc BC, and as you can see, BC here, the value of this changes as B gets closer to C and B gets farther away from C. So this is the measurement of the arc, but let's take a look at the measurement of the angle ABC. And most people will think, oh, it looks to be the same, but actually the relationship is that the measurement of the arc and the measurement of the angle are not the same. And so, but there is a relationship between the two. And if you've already noticed that whatever this angle is, ABC, to figure out what the arc is, we multiply it by 2. Or to wherever this arc measure is, to figure out the angle, in this case, we multiply it by 1/2. And so that's the relationship. As you can see, the measure of this arc AB is going to be equal to double the measure of angle 1. And if we're looking over here, we can also see another relationship is that the measure of angle 2 is going to be equal to 1/2 the measurement of which arc, because now we're dealing with a different arc. And the arc that's going to be, it's going to be 1/2 of is this major arc over here, arc BCA. Now what happens when two chords intersect inside a circle where their intersection is not the center? Well, that means you no longer have a central angle and you don't have an inscribed angle. You have just these angles based off two chords intersecting. And let's see the angle relationships and the arc relationships. So here we have arc AKD, and here we have arc CGB. So they're opposite arcs. And as you can see, they're different angle measurements even as I move them around. So they're not congruent arcs like one would think, because the angles may be congruent. But let's take a look to see how they relate to the actual measure of the angle. And as you can see here, there is something going on here, and it looks like this angle measurement of AED and CEB is somewhere in between the measurements of the two arcs. And if you said that or noticed that, you're absolutely correct. In fact, the angle measurement is an average of this, the sum of the intersected arcs. So they're taking the intersected arcs and taking the average of them too, which means adding them up and dividing them by 2. Let's see if that holds for another set of of angles inside here. So as we can see here, this is 114 DFB and this is 71, but the measure of this angle is actually in between 1.26 and 1.114, which lets you know that that's relationship holds. So this relationship is that the measure of this angle 1, or this opposite angle 1, can be found by taking the average of these two arcs that do not measure the same length. So in other words, the measure of arc DC plus the measure of arc AB, and divide that by 2. And for here, for the second angle, as we can see here, angle 2, we're going to be using this arc and find the average of those two by adding up the arcs and then dividing by 2. And this video is a little bit longer, but I'm going to have to end it before we can get down here to going over 10.13, but that's okay because 10.13 doesn't have you filling stuff in, but I encourage you to take a look at that. All right, that's it. Bye-bye.